Okay, so I'm going to talk about MOSAIC. As Michael said, it stands for Mars Orbiter for Surface Atmosphere-Ionosphere Connections. And I'm something of a figurehead for a large effort involving approximately 50 scientists from across the UN. So just in case you fall asleep later, I'll just give an upfront 30-second summary. What is MOSAIC? So MOSAIC is a mission that plans to unveil the complete Martian climate system from both mesoscales to planetary scales, and from the subsurface to the exosphere. And the way we plan to do this is with 10 coordinated, mostly small satellites, making simultaneous measurements of the Mars climate system, many of those measurements for the first time. And it's different options range from the sort of New Frontiers class up to the flagship class. Our team here, Nathan Barba and Ryan Woolley, have been sort of leading the systems and mission design sides. And we have a number of science leads for each of the different science investigations, which I'll get into soon. And then another 38 co-investigators and collaborators from different countries. So this was a pretty... Just go into some of the science background and the motivation. The C in MOSAIC stands for the connections between the different parts of the Martian climate system. And even after 2 continuous decades of investigation, we really don't understand how matter and energy move throughout the Mars climate system in 3 fundamental and connected ways that are represented by these 3 questions here and also shown in the figure on the right. First, we know there's a large annual cycle of movement of water and CO2 between the atmosphere and surface ice reservoirs in the polar regions, but we don't understand the numerous processes, both in the shallow subsurface and the boundary layer and on the surface itself, that drive surface pressure variations and ice distribution. Second, we don't understand how the lower and middle atmosphere responds either on mesoscales or on global scales diurnally, and how that diurnal cycle changes with season to changing insolation from the sun due to Mars's elliptical orbit and axial tilt. And in particular, we've observed neither the diurnal cycle nor directly measured wind except from a small handful of surface locations. And third, we don't adequately understand the myriad different ways that Mars's upper atmosphere is driven both from below by the lower middle atmosphere and also from above by the space weather environment. So this is the sort of the glue that ties the MOSAIC concept together, understanding these connections between different atmospheric regions. Can I move to the next slide? Yes, okay. Now, Wendy covered this pretty well, so I'm going to breeze through it and just say that there's a lot that we don't know about the processes that govern surface pressure and ice distribution on Mars, and that we therefore need simultaneous monitoring of shallow surface ice and subsurface ice and atmospheric conditions to understand these processes. And that, as she said, SAR and thermal monitoring would detect these changes that result from these interactions. Okay, I'll move on. Martian winds have been a major mystery for a long time. Our knowledge of global winds has been indirect. It's been estimated from the temperature measurements that we've made, and most of those temperature measurements have been made at a fixed local time too. And then the thermal wind relationship that determines how wind responds to different changes in pressure. And while this has been useful to understand global dynamics, this approach it's inappropriate for winds in the tropics, where the wind patterns are more complex, and it's too imprecise for winds in synoptic systems at all latitudes, like the high latitude low pressure systems pictured there above on the right. And so our study considered the trade-offs of different kinds of instrumentation types for both winds and other important associated measurable quantities like aerosols, temperatures, and trace gases. In addition, because of the extreme nature of global dust events, having a global perspective, similar to what you call a geostationary on Earth, areostationary on Mars, gives you the kind of perspective necessary to understand the origin and development of these storms. So this is something else that we looked into in plenty of detail as well, how to get this perspective to boost our understanding. In addition, there's significant lower upper atmosphere connections that up until recently had not really been sufficiently appreciated. In particular, we see a very strong seasonal variability in hydrogen escape rates from Mars, about a factor of 10 or even up to 20. And When this occurs, we observe water at higher altitudes than expected, usually coincident with the dust season. However, the observations have been limited to the terminator, so we don't understand the diurnal pattern of that water vapor. And with multiple competing hypotheses for how the water is transported from the surface up through the atmosphere to high altitudes, and then how it escapes, we need to make simultaneous measurements of the lower atmosphere, thermosphere, and exosphere to understand this important process, which was a major driver of Mars climate evolution over time. And then lastly, when that the lower atmosphere material is transported upwards into the ionosphere, and above it becomes ionized, it becomes part of Mars's rich and complex so-called hybrid magnetosphere, called that because it shares properties of both intrinsic magnetospheres like the Earth and induced magnetospheres like Venus. And most of this richness, for example, magnetic fields, plasma flows, can only be sampled in situ. It can't be measured remotely. And while the MAVEN mission has certainly provided a wealth of new understanding, its plasma measurements are fundamentally limited by its single platform. So we need to make these measurements that are both coordinated and also multi-point to untangle spatial from temporal variability, to measure the response of the system, for example, the rate and pattern of ion escape to changes in upstream solar wind conditions, not with a time lag of an hour or more like we're stuck with a single orbiter, but in real time. And then also to unravel the chain of cause and effect as solar UV and the solar wind energizes ions to escape and precipitate. So that's the science motivation for MOSAIC. Now, just to jump into science traceability, and I've tried to capture the traceability and the processes on one chart here. So let's go start at the far left. The overall major science goal of MOSAIC is to understand Mars's present-day climate processes and their interconnections from the subsurface up to the solar wind. And that then leads to four or five different mission objectives here. And starting at the bottom, as I've said, to characterize the volatile cycling between the subsurface, surface, and atmospheric reservoirs, to characterize the structure and dynamics of the lower middle atmosphere on these different scales and understand its variability, to correlate variability in the thermosphere, ionosphere, and escape rates to both drivers from below and above, and then to characterize these fields and plasma flows. And each of these different objectives relies on more than one investigation, and I've listed the investigations here 1 through 8. It's ice distribution, atmospheric structure, the diurnal behavior of the atmosphere, the thermosphere, the ionosphere, the exosphere, and the neutral escape that happens there, the magnetosphere, or the plasma environment, and the ion escape that happens there, and lastly, the space weather environment that drives it. So this is how we arranged the traceability, and as you can see, multiple investigations are necessary to address the objectives, and all of the objectives are necessary to achieve the overall goal in its entirety. As both Clive's presentation and also Wendy's as well has shown, there's additionally significant exploration relevance to the MOSAIC investigations here. And so here our goal is to identify hazards, to characterize resources, and to demonstrate technologies to enable the human exploration of Mars. And here we have a few different objectives. As Wendy spoke about, the extractable water ice resources is an important one. Also to characterize the atmospheric state with sufficient sampling and cadence to allow accurate data assimilation and therefore weather forecasting. To characterize neutral winds in the mesosphere and lower thermosphere and the effect those might have on operations like EDL or perhaps even aero capture. To characterize the Mars ionospheric state sufficiently to determine its likely disruptive effects on things like global positioning and communications. And then lastly, the environment of radiation in Mars orbit that astronauts will have to deal with when they are there. And not to read what's there on the right, but it's the The investigations of MOSAIC fulfill 7 different high priority knowledge gap filling activities identified by the precursor strategy analysis group there, as shown on the right there. So there's significant relevance of these measurements to exploration, and just as Wendy said, without having to actually change anything, this sort of comes for free if you are able to fulfill these investigations. Okay, I'll jump through this quickly. I'm going to go through each of the investigations quickly, showing the measurements, the instruments, and the platform that they need. Wendy basically covered all of this, so I don't actually need to spend any time on it. So I'll just jump right on to investigations 2 and 3, the lower middle atmosphere. So here, the important measurements that we're going to be making are vertical profiles of temperature, winds, dust, both water and CO2 ices, and water vapor, ozone, and other trace gases, and also surface temperature and pressure. And for this, the instruments are LIDARs, submillimeters, sounders, a thermal infrared spectrometer, radiometer, and a near infrared spectrometer. And these all need to observe from a near polar, low altitude circular orbit. This is an example of several of these quantities shown from trace gas orbiter data from paper by Fedorova this year. As well as measuring the vertical structure, we also need to understand the complete diurnal and geographic behavior. And I've highlighted both winds and this diurnal behavior in blue because these are brand new measurements that have not been made before. And so here the idea is to get global synoptic views of the column opacities and abundances of these same quantities that were listed for investigation 2. And to do this from 2 different platforms, one to have that global view so you can see sort of almost a full hemisphere of the planet at once, that's the areostationary view, but then also to have different near polar low altitude circular platforms at different local times to examine how the vertical structure changes over the course of the Martian day. And investigations 4 or 5 are what we would think of as the upper atmosphere, the thermosphere and ionosphere, thermosphere being the neutral component, ionosphere being the ionized one. And here our required measurements are to measure the vertical profiles of the density and temperature of the primary atmospheric species, as well as horizontal wind velocity. And wind has never been measured before in this area in any systematic way. There's been a little bit of work done by MAVEN, but not systematic. And here we need a wind interferometer, an FUV, MEV spectrograph. And again, the best platform is that near polar low altitude circular orbit. The ionosphere, the idea here is to measure the 3D global structure of the ionosphere. And the measurement is vertical profiles of electron density, and to do this in 2 different ways. One via radio occultation between an elliptical type, sort of MAVEN type orbit, and a polar type orbit, more like an MRO orbit, and then also using in situ measurements with a Langmuir probe to ground truth those occultation measurements here. And shown here are just the folks that have made up those different science groups. There's been a different group of scientists assigned to each of these different investigations. Going on to investigation 6, this is the exosphere. This is the part of the upper atmosphere where the escape occurs. In particular, this the neutral escape of both oxygen and hydrogen. So the idea here is to measure the vertical profiles of density and temperature of both oxygen and hydrogen using an FUV spectrograph. And here, the best platform, the best viewpoint is an areostationary viewpoint here. These are figures here from the initial very long capture orbit of MAVEN that briefly, just for a few orbits, gave us this kind of perspective before MAVEN had to lower its orbit down to its final science orbit. So this kind of perspective is something that we would like to get systematically to monitor how the rates of hydrogen and oxygen escape change with conditions in both the thermosphere and the lower atmosphere. And lastly, investigations 7 and 8 are concern ionoscape and the magnetosphere and how that's driven by the space weather environment. And here the idea is to make, for investigation 7, to make measurements of magnetic field, both strength and topology, and also the fluxes of both light and heavy ions, both across the Mars bow shock, the magnetic pileup boundary, and throughout the magnetosphere. And the new thing here is from multiple locations simultaneously to untangle the spatial from temporal variability that I spoke about earlier. Here the instruments are magnetometers, electrostatic analyzers, and both for electrons and ions, and a Langmuir probe, as well as actually electric fields got left off this chart, but electric fields also too. And lastly, to measure the space weather drivers that kind of drive the whole upper atmosphere and magnetosphere system. So essentially measure any of those same quantities, but in the undisturbed upstream solar wind, in other words, outside of Mars's bow shock. Okay, so the concept study process that we went through, I'll just spend a few slides talking about that, much as Wendy did. We divided up our science team into these 7 different groups. This enabled sort of focused work to happen within the groups among people who are experts in those kinds of measurements to make. As you can see, I'm starting from the upper right, the subsurface and surface ice, the lower and middle atmosphere, the ionosphere, the radio science sort of had its own separate group because of the unique challenges there, the magnetosphere and space weather environment, and the thermosphere. And then also there was a sort of a multidisciplinary group to look at lower and upper atmosphere connections as well. And then everything was coordinated through myself and Dave as the leads. What we did starting last fall was for each of the investigations, each of those 8 investigations I talked about, we defined the measurement requirements, the quantities to measure, the range, accuracy, resolution, the coverage, both spatial and temporal, the physical parameters versus observable quantities, which aren't always the same thing, baseline versus threshold. And we also defined instruments that could meet those measurement requirements. This is not supposed to be read here, but this is just an example for investigation 2. In other words, we just compiled all the measurement requirements in 8 different spreadsheets for the 8 different investigations. And this will all go into the final report, all this gory detail in Appendix B of the final report. And then for each of those instruments, we then went and defined what their requirements were and what their key characteristics were. So descriptions, names, platforms, the measurements they would make, their suppliers, TRLs, fields of view, mass, power, volume, different accommodation constraints, the resolution, data rate, and cost, etc. So we compiled lots of instrument requirements, and this was important because this was to guide the JPL concept study team to help us actually flesh this out into a real mission concept. We made quad charts for all the instruments. This is just an example for the wind interferometer for the thermosphere, where we had the science in the upper left, the requirements of the measurements in the lower left, the resource and accommodations in the upper right, and any particular TRL, story, heritage, etc. on the lower right. And so this was a really handy reference for the JPL folks to use to figure out how to accommodate these instruments on the different platforms. And it started out with an A-team study at JPL, so to just examine the trade space, and this team produced the sort of architecture building blocks that were relevant to the trade space, and also to help define the technologies that would enable parts of the trade space over the span of the decadal survey. An example here being optical communications and the high data rates that allows. We looked at 13 potential architectures, and we quickly narrowed them down to 4. So we did have a chart like the one Wendy showed. And then this was the trade space of architectures for TMEC-C, which is the CubeSat or small sat version of TMEC, and then the full TMEC to examine in detail. And MOSAIC required 2 different sort of week-long studies, both TMEC-C and also TMEC, due to the large size of the constellation. So let's go look at the architecture now, how these different pieces fit together. And before we get into sort of what they are, it was guided by which platforms were needed to accomplish which of the investigations. So we have 8 different investigations here, each with identified instruments, which have requirements for spatial and temporal coverage. And we achieve this coverage by placing the instruments on 4 different kinds of platforms with different orbits and different numbers of spacecraft per platform type, as shown there on the bottom, with 1 mothership, 4 areostationaries, 3 different small polar platforms, and 2 different elliptical orbit platforms. And so this is sort of the visual slide showing what that architecture is. So the left half is MOSAIC by the numbers, the 10 different spacecraft elements. You can see them stacked up there on inside a Falcon Heavy fairing with the mothership on top and 2 different ESPA rings underneath to accommodate the 10 instruments. The 10 spacecraft with a total of 48 different science instruments, not different ones, but just distinct ones, distinct instruments, not different instrument types, with 3 different orbital perspectives, all on 1 launch vehicle. And we show the telecommunications architecture there on the right, whereby the Areostationary spacecraft, shown there in orange, will talk directly to Earth. They were just too far away from the mothership to have that be an efficient way to communicate. But the small polar orbiting satellites shown there in purple, and also the elliptical orbiting satellites shown there in green, do speak to the mothership and relay their data back through the mothership's large antenna. Okay, so let's go through the platforms. The mothership was envisaged to be a large solar electric propulsion orbiter with it's about 3.7 tons in a similar orbit to the Mars Reconnaissance Orbiter. And this addresses, first of all, investigation 1 via the radar sounder. This is all about mapping and inventorying the ice. Secondly, this gives us the platform we need to measure the important the vertical profiles of the important atmospheric quantities that have to be measured there as well. And lastly, also, it gives us the perspective on the thermosphere to measure the structure composition and the new measurement winds in the thermosphere. So these 3 together are the investigations addressed by the Mothership platform. We also did look at a mini mothership option. Just because the mothership was so large, we decided to look at potential D-scopes. So there is a much smaller version of this that's only about 1/5 of the mass. And it unfortunately loses all of the new measurements, the radar sounder, the submillimeter, the wind LiDAR, and the Thermosphere wind interferometer, but it does preserve the global coverage of atmospheric connections and the constellation aspect of MOSAIC. So we looked at this too. Going on to the Areostationary platform, there's actually 2 different types here, and this was driven partly by the different needs of the investigations that want to be there. The 2 types are a so-called small orbiter with about a 565 kilogram mass, and then a much smaller so-called mini areostationary orbiter with a wet mass of only 93 kilograms here. And the investigations that are accommodated by this, well, first of all, there's investigation 3, which is the diurnal coverage with the instruments shown there. And that needs all 4 of these platforms because it needs to see the planet in its entirety in order to understand those diurnal processes happening. We only need 1 of these to investigate the exosphere. The FUV UV spectrograph just needs to be on 1 of them, so that's going to be on the larger one. And then the space weather monitoring platform wants to be on a minimum of 1, but preferably 2 of these in order to have 100% coverage of the solar wind here. So it just needs to be outside of the Mars bow shock, which an areostationary orbit is about 70% of the time. And this is a simulation of the heliospheric environment that we're trying to understand, and the measurements that this platform would help to constrain that too. Okay, so these are the 3 different investigations that the Areostationary platform can do. Then we had a little bit of fun. Our mission designer thought that Areostationary sounded a lot like Oreostationary, so he made this fun slide here, and I will include this in final one because I just find it funny, especially the double stuff Oreo. Okay, so next, the Polar Platform. These are small spacecraft. They're not quite CubeSats, but they're definitely small with just the limb radiometer and the near-IR spectrometer. The idea here is to place them in these sort of complementary orbits with the mothership so that eight local times of day are sampled at the same time. This is the other half of Investigation 3 with the Polar Platform, allowing us to see how the vertical structure changes as the day goes by. And then this also gives us a great opportunity to perform radio occultations. And shown here, this figure is a simulation of the coverage in latitude and longitude of radio occultations between both the elliptical spacecraft and the polar orbiting spacecraft. And as you can see, it gets really fantastic coverage. This is both of the ionosphere, but also of the pressure and temperature from the surface up to about 40 kilometers. So this is a capability that we've never had before, which would really be a game changer also in terms of understanding how the atmosphere varies. And here's just the two together. And lastly, the Elliptical Platform. This is a small spinning spacecraft. The best analogy is probably the 5 identical spacecraft Themis mission. It's been orbiting Earth and now the Moon for a decade or so. And so here, this allows us to get close enough to the planet to measure the ionosphere and the the ion precipitation and escape regions in situ, but also cross the important plasma boundaries to understand how the global structure of the magnetosphere changes with changing upstream conditions. Okay, so how do we get this constellation to Mars? So Ryan Woolley did a lot of work here. The idea is it all launches on one spacecraft, and then soon after the interplanetary injection, there's a separation where the mothership and the upper ESPA ring containing the small polar CubeSats and the elliptical orbiters separate from the other ESPA ring that just has the 4 Areostationary spacecraft. They make their way separately to Mars over the course of about a year and a half. Then they arrive at Mars and spend not quite a year all getting into the orbits that they want to get into. The Areostationary spacecraft have to spread around in longitude. The mothership drops off the elliptical satellites in their elliptical orbit, and then it lowers its orbit propulsively, and then drops off the polar orbiting CubeSats that have a small bit of propulsion in order to get into their different local time orbits. And the idea is to have a 2 Mars year primary mission to at least get some idea of the interannual variability of the climate system, although we'd of course like to be around there much longer. This is a movie. I really tried to get a higher quality version of it working within the PowerPoint, but it didn't work. So this is just a GIF showing the perspectives of the spacecraft, both polar, elliptical, and areostationary orbits. So you can see that coverage there. So an important question that we wanted to ask ourselves was, how modular is MOSAIC? Because this is a big concept with a lot of different pieces to it, and it's important to know which pieces of it you potentially lose and how acceptable that might be from a science perspective if you were to descope different pieces of it. So this is that same goals, objectives, and investigations chart here shown with green check marks if we have all of the pieces in place. And just to go through a few examples of, say, what you might lose. If you go to the less capable mini mothership, you lose all of the ice. Of course, because you haven't got that big radar. You lose all of the winds, which gets you a partial loss of pieces of investigations 2 and 4 as well. So this is just an example there. Another example is if we lose the polar platform, we would lose some of our diurnal behavior coverage, and we'd also lose the radio occultations. So we'd lose bits of investigations 3 and 5, and therefore also have we wouldn't fully address the science objectives there shown in orange. We lose the elliptical platform, we lose also the radio occultations, but also all of the magnetospheric goals as well. Another last point to make is that we don't think NASA has to pay for everything here. The full version of this concept is definitely flagship class. But because it's somewhat modular, we think that different elements of the architecture could be contributed. For example, another country might want to contribute the 3 polar CubeSats, and that would count as an element. Also, operational coordination between the elements, we do need it for the comms, and we need it for the occultations, but the measurements themselves can just be made and then can be analyzed later. So in that sense, the coordination doesn't need to be necessarily extremely tight. Lastly, some either currently existing or planned or in development spacecraft could partially fulfill some of these MOSAIC investigations. And I put an asterisk there because existing assets are getting old, particularly that first line there, Mars Reconnaissance Orbiter. And also, the MOSAIC objectives and overall goals are only achieved with a simultaneous observation, so simultaneous performing of these different investigations here. But there are some sort of partial overlaps here, and the darkest green is basically just as good as MOSAIC. Then light green is not as good. Then yellow is less good, and orange is still useful but less good again. And there are several missions both orbiting Mars now. You can see the MAVEN particle and fields package, the MAVEN imaging ultraviolet spectrometer, the trace gas orbiter instruments, and then missions launching either this year or soon. The Emirates Mars mission has 3 instruments that are definitely relevant to this. The Chinese mission that's launching this year has some instruments relative to the magnetosphere and the space weather environment. The ESCAPADE mission, which is currently in phase B, it's not confirmed yet, but that would accomplish a lot of the magnetosphere goals. There's also the Japanese mission, MMX, which will be in Mars orbit for about 3 years, making measurements that are relevant to some of this too. And then, of course, there's the concepts like the ice mapper that Wendy spoke about, and also the compass discovery proposal that would fulfill much of the ice mapping requirement here. Almost done. So costing. So Wendy touched on this already, but the JPL cost experts, they've evaluated the mass, duration, complexity, and they've developed these likelihood cost S-curves. And we're using 2 different cost paradigms, and this is sort of because of the small sat nature of most of the MOSAIC constellation. One, we're using the standard JPL cost models based on previous projects, but we're also going to quote more of a simplex, small sat approach with common off-the-shelf parts, new space manufacturers, these small companies that do things sort of in a more nimble way, with associated risk, of course, and also minimal redundancy. We're not ready to release the final cost numbers, but the options do legitimately span the new frontiers up to flagship class. So why would we do MOSAIC? It's because the interconnections between the surface, the lower and upper atmospheres, and the ionized and space environment are stronger than previously thought and poorly understood, and because Martian explorers will need water, air, fuel, weather forecasts, health, and safe EDL. And so we're hoping that we can write a detailed report motivating this 10 spacecraft constellation to make these unprecedented simultaneous measurements of the Martian climate system, looking at the post-2028 timeframe. And I will leave it there, and I will take questions either now if we have time, or by email later. So thank you.